Good morning, everybody. Welcome to our ESM All Hands webinar, and we are continuing with the mini-series to learn more about the screen model and screen simulation. Today, we are having Dr. Chris Terai and to talk about the screen simulation in multiple perspectives. Chris, please go ahead.
Thank you, Ian, and good morning, everyone, and thank you all for being here today. And so 2 weeks ago, and the last All Hands, Luca gave a very nice presentation talking about the computational performance of Scream. And so what I'm here today excited to share with you is to follow on talking about Scream's climate. I'll start off with talking about how Scream represents the present day climate. And then I'll move on to more recent results looking at Scream's climate sensitivity. And so the first thing I want to acknowledge is everyone who's listed on here as a co-author on this presentation, because the running of the simulations, the evaluation, and then fixing the model has definitely been a team effort that's been performed by the Scream team as well as collaborators. And so I wanted to start off by acknowledging the fact that I've had the climate in quotes, and that's because Scream is an atmosphere-only model, and we haven't still run, or we're just starting to test out being able to couple it with an interactive ocean and sea ice, and so we haven't run that coupled simulation yet, as well as the fact that we actually haven't run that long when it comes to the simulation length. And so that gets to the biggest challenge when it comes to running and evaluating Scream. It's computational cost, even though it's amazing that we've been able to make use of the world's fastest supercomputer with the code changes to Scream. It's still a very expensive model because we have a horizontal resolution of about 3 kilometers, and then it's got 128 layers in the vertical. And so that's been our main constraint driving our simulation strategy. And so, but the fact that we can actually run on machines like Frontier have made it so that we've been able to rapidly expand our simulation length. And that's what I'm showing as a graphic down here on the bottom, where we started about 3 years ago running the Fortran version of the model, Scream V0, and that was 40 days in length. And that seemed like a major undertaking. And it was our submission to the Diamond 2 model in a comparison. Since then, we've run 4 times of that simulation using the Scream V1 model, and that was led by Aaron Donahue, the 4 season simulations that I'll be talking about later. And then more recently, just last year, we've been able to run 13 months continuously with the Scream simulation, both in the present day using prescribed SSTs from the present day, and then another paired simulation where we've increased the SSTs by 4 Kelvin. And so that's the Potter simulations that I'll be talking about later. A similar type of 13-month paired simulation will be used to look at the aerosol sensitivity. They're the aerosol simulations that are planned for this year. And then we're going to increase the simulation by another factor of 10. And that's being conducted by Ben Hillman. That's decadal simulations that gets us to 10 plus years. And so there's been a rapid increase from 40 days all the way up to 10 plus years just in the span of about 3 plus years. And so we're increasing our simulation length, but if you compare it to something like the coupled simulation where it takes a 2,000 year spin up, it's quite short. But despite that, we do think that we can learn a lot about at least what the atmospheric climate will give us, what the atmosphere phenomena gives us in Scream, because fortunately many of the atmospheric processes occur on timescales of days, within less than a week, and that's shown on the, just to give you a visual representation on the top right. We're looking at atmospheric phenomenon as a function of spatial scale and then temporal scale, and where I've drawn an orange line is about where 1 week would be. And you can see that there's a variety of atmospheric phenomenon that we can actually study even with the 1 week simulation. On top of that, what previous studies empirically have shown is that if you look at simulations from Hindcat simulations and you look at the model error, they actually manifest themselves in the manifest the climatology error in just a matter of few days. And we can actually see that in our 4 seasons simulation. And what we're looking on the bottom is the global mean water vapor path. And we've found that the Scream has this bias of having too dry of an atmosphere. And so across our January, April, August, and October simulations, you can see that Scream, which is in blue line, compared to the reanalysis, which is in black. The Scream has a drier atmosphere, and it seems to be consistent across all 4 seasons. The second thing to notice is that the fact that these biases tend to show up quite rapidly, and they actually tend to tail off within less than a week. And so we can expect to see with our simulations, especially now that we've run 40 days, 40 day times 4, and then 13 months, that we can start to learn a little bit about Scream's atmospheric phenomenon and how it represents the climate. And so that's what I'll be talking about, starting off with the highlights in terms of the phenomena that Scream does represent quite well, and those that we actually expected, given its resolution and also the previous literature. And the first thing to note, the obvious thing to note, is that it represents the qualitative aspects of mesoscale organization that were previously unresolved quite well within the model. Start on the top right is a snapshot from a mesoscale convective system over the continental US. And then on the bottom right is one of a tropical cyclone, how it rapidly develops into a category 3 tropical cyclone over the southern Indian Ocean. Another aspect of Scream aspect of the climate that we expect it to do well, and it does fairly well, though there are areas that we can improve on, is the diurnal cycle of precipitation. And that's shown on the bottom left figure right here. We're looking at GPM IMERs, so satellite retrievals, and then Scream on the right. And we're looking at the diurnal cycle of precipitation, the composite, over 4 different boxes that are shown here over the continental US. As you go from black to purple to green, we're moving eastwards. And you can see, if you look at the GPM IMERs, the peak of the precipitation shifts later and later in the day, and that's reflecting on some of these systems that move eastwards, propagate eastwards. Scream, not perfect. As you can see, it's a little bit early over the mountains. The amplitude is a little bit higher, but you can see this slight shift as we go eastwards of the mountains, the high plains, and then perhaps over the mid plains, where Scream seems to struggle. We're still looking at whether it's a large scale bias that's showing up, but is the low plains, where it doesn't quite capture this later peak. But in general, if we look at different areas within the globe, Scream's diurnal cycle of precipitation is much improved from, say, one that's a conventional climate model with that relies on deep convective schemes. So that's the improvements that we expected to see. There were some surprises in terms of what Scream does well with, and one of them was the diurnal cycle of boundary layer clouds, and we can actually evaluate that with arm retrievals and observations, and that's because now we're at 3 kilometers, where we think that the scales at which the observations are made are close to what Scream actually is able to resolve. And so what we're looking at here is the arm site over the tropical Western Pacific over Darwin. And we're again looking at the diurnal cycle, the composite diurnal cycle of, this time it's the cloud fraction, so the high resolve cloud fraction. And then the top is Scream V1 and the bottom is ARM. And apart from the fact that Scream seems to have mean state biases in the amount of clouds over this region, you can also notice this growth of the boundary layer clouds that we see in Scream that we actually see in observations as well. And this is actually not the case across all storm resolving models to actually capture this diurnal cycle of boundary layer clouds. And we think that it's because of our inclusion of shock as one of the processes that we have in Scream. Other phenomenon that Scream seems to capture well is the atmospheric rivers. It gets the latitudinal distribution as well as the strength of the atmospheric rivers when we compare them to, say, what we'd estimate from reanalysis. And one, I think, lucky and surprising result is that even Scream is a very expensive model, and so it's very difficult to tune Scream. But despite minimal tuning, we've been able to capture the global mean top of atmosphere radiative imbalance quite close to what satellite Ceres in this case captures. And that's shown on the bottom left plot here, where we're looking at the latitude distribution of the net top of atmosphere radiation imbalance. And you can see the seasons are represented in different colors. And in the solid line is SCREAM, and then in dashed line is Ceres. And you can see that it's able to capture a lot of the shape that we'd expect, the latitudinal shape that we get in the imbalance, though there are some regional biases if you look a little bit closer. What I wanted to point you to is the global mean net radiation imbalance, which is quite important for the climate. And you can see that if you look at these global means that are shown as the numbers right next to SCREAM and Ceres, they're actually within about at least 2 watts per meter squared. And that's been surprising, and we've been lucky with how we've gotten this global mean top of atmosphere radiative imbalance. There's still room for improvement. And so that gets me to the next part, which is the things that SCREAM struggles with. One of the persistent biases or the issues that we've seen within SCREAM is this, what we've been calling popcorn convection. And this is to do with the organization of convection, where if you look at a snapshot of precipitation rates, such as shown on the top right here, it's a snapshot over the tropical West Pacific. You can see this is the precipitation rate, and you can see it's more speckled. It's not as organized as we'd expect if you were to, say, look at satellite retrievals. And so that's been one thing that we've been doing lots of testing. We've been able to improve some, and I'll talk a little bit about that later, but we still haven't been able to completely fix this issue. Another bias that we see within SCREAM is this lack of mid-level clouds and humidity. And again, to show this, I'll use an arm site comparison, and this time over Go Amazon. And we're looking at the diurnal cycle of clouds again. And if you look at ARM, you see this mid-level cloud fraction showing up, which is completely missed within SCREAM. And so that's one location. Do we see this all over the tropics? Yes, we've also looked at CloudSat retrievals, but it also shows up if we look at the humidity field. And so that's what's shown on the left here. We're looking at the latitude on the x-axis. On the y-axis is the pressure level, so it's the vertically resolved humidity. And what we're looking now at is the SCREAM V1 minus the ERA 5 reanalysis humidity differences. And the one thing that's quite striking in this is over the tropics and perhaps some parts of the subtropics. In this mid to lower troposphere, we have this very dry bias we see in SCREAM. And I'm showing this for January, but we see this across all 4 seasons. And that's flanked with this a little bit of a moistening trend, as well as its moisture in the boundary layer and also the upper troposphere, but it's too dry here. And the running hypothesis that we have so far is that it's because we're missing this congestus clouds. SCREAM's struggling to represent congestus clouds, the vertical development as it goes from shallow convection to congestus and then to even deeper systems. We're missing that stage such that we start to develop the clouds, and suddenly, if enough instability builds up, the clouds shoot up, they detrain at higher levels, and so we don't have an issue with high level clouds, but we miss these mid-level clouds. We also see within SCREAM we've made some improvements, but we see that SCREAM also has a warmer near surface land temperature that I'm not showing here. And along the way of trying to evaluate SCREAM, we've also learned a few lessons along the way. One of the things that we noticed from early on from the V0 version of the model, and now we saw it also in the 4-season simulation, was the fact that the 10-meter wind speeds were biased strongly. And so that this is a spatial map, and if we look at where it's just stronger compared to reanalysis, we see that it happens a lot over topography. And so when we first designed SCREAM, we didn't think at 3 kilometers that the turbulent mountain stress scheme was necessary, but we tested out a configuration where we actually added the TMS and compared it to default version, and we can see that if by turning on the turbulent mountain stress scheme, we were actually able to ameliorate a lot of the wind speed biases that we originally had. So what we learned was that even at 3 kilometers, we do need our turbulent mounting stress scheme. Another thing that we've learned, and this was in improving our popcorn convection, was that when we were running various tests, removing the subgrid variability of the microphysical tendencies helped reduce this popcorn bias. And so the way we've been trying to track popcorn has been to look at the size of different rain objects that we see in SCREAM, and that's, so this is a PDF of the rain size on the x-axis and the histogram actually on the y-axis, and then you can see that we at SCREAM V1 had this large peak when we compared to, say, GPMI merge, which is this black line here, had way too many of these small precipitation objects. When we moved to SCREAM V1, one of the big changes we made was to remove the subgrid variability. We saw an improvement, though there's still a ways to go. And so hopefully I've given you an overview of a bit about what we're doing right well, what SCREAM is able to represent well, but of course there's a lot of biases. But we are now able to run SCREAM for 1 year. And so one of the questions is, what can we learn from a 1-year simulation? And I think one of the big questions that Peter Caldwell has been interested in is to learn about the climate feedback, since that's there's a large uncertainty across the CMIP class models, and previous studies have noted that the deep convection scheme has been a large cause, a large root for that spread in the cloud feedbacks. And so to calculate the climate feedbacks, which is defined as if you have a radiative forcing at the top of the atmosphere, how it determines how large that temperature response of the Earth system is. And that's the climate feedback that gives you a sense of how strongly the system actually perturbs, the temperature perturbs to this forcing. And that climate feedback typically requires running a coupled simulation. You increase the carbon dioxide levels, say by 2 times or 4 times, and then you have to run out to hundreds of years. And that's not possible yet, or ever perhaps, with SCREAM 3 kilometers. But what previous studies, starting with SES in 1990 and then Ringer et al. In 2014 had found was that this feedback parameter, where most of the uncertainty is coming from the cloud feedbacks, can be cheaply and reasonably computed using these fixed SST experiments where we prescribe the SSTs with the present day, and then you run a simulation where you've perturbed delta T. And then based on that, we can read off what the change in the top of atmosphere radiation is, and from that derive what lambda is. And that's kind of what's shown on the bottom left, where we're looking at the fixed SST, the cloud feedback parameter, and you can see if you compare it to a coupled simulation, and we're going to compare the cyan dots, they tend to correlate highly, plus they're also on the 1-to-1 line as well. But that's with 30-year AMIP simulations, and 30-year AMIP is also still out of reach for SCREAM. But fortunately, Each and co-authors have found in their recent study is that you can actually do that credibly using a single year of data. And that's what's shown on the bottom right plot, where you see that if you use 30 years, you get this amount of correlation across the models when it comes to comparing the feedbacks from the coupled system and a coupled simulation and the AMIP simulations, but you can get similar type of correlations even with 1 year of simulation right here. What they also found was that the best results come from an ENSO neutral year. So what we did was run SCREAM for 1 year, 13 months actually, starting off with August of 2019 and ending to the end of August 2020. And that's an relatively ENSO neutral period. And we ran 2 sets of simulations, the baseline present day simulation and the one with plus 4K, and calculated feedbacks. And that's what I'll be showing next. And so the global feedback that's calculated from those simulations from SCREAM 3 kilometers is negative 1.1 watt per meter squared per Kelvin. What's shown in orange is a companion simulation that we ran at lower resolution. It's SCREAM 12 kilometers, and you can see that it gives a different global net feedback. Now, those numbers might not mean much to many people, and so what we've plotted here on the left in the light x's, gray x's, are the total feedbacks calculated also in AMIP simulations, but from CMIP6 models. And you can see that spread from all these models, and you can see that first off, the SCREAM simulations are within that bound. So running at 3 kilometers without deep convection doesn't give you a completely different global mean feedback, but it does, if you look at the 3 kilometer model, which is the default setting for SCREAM, it does tend to have one of the highest climate feedbacks. And you can ask the question, where is it coming from? And so we can break down the global net feedback into its Planck, which is the sigma t to the fourth, negative feedback, the lapse rate feedback, the water vapor feedback, the albedo feedback, and this albedo feedback doesn't include changes in the sea ice because the sea ice are prescribed, and then the cloud feedback. And we can see that most of these feedbacks tend to lie quite close to what the CMIP6 mean is, except for the cloud feedback, and that's quite positive, especially in the 3 kilometers. We can ask then the question, is it coming from the short wave or the long wave partition of the feedback? It actually comes from the short wave part of the feedback, where it has quite a SCREAM 3 kilometers has a strong positive shortwave cloud feedback. And so just to summarize here, the feedbacks coming from SCREAM lie within the range of the CMIP6 models, but if you actually look at the total feedback, it is one of the strongest ones, and the cloud feedback is the reason for that, and has one of the strongest among the CMIP6 models. What's been interesting to also, I think surprising to see, is also there's a large resolution sensitivity when it comes to this cloud feedback, and that's what we're looking at more closely, trying to understand why it also occurs. But we can take this net feedback and ask the question, what is the equilibrium climate sensitivity? And in this case, it's an estimated climate sensitivity, since we actually have to do a little bit of approximation. But we can take the total radiative feedback from the SCREAM 3 kilometers, about negative 1.1 watts per meter squared. And then we need to do an adjustment there's an adjustment between what you get, the net feedback in the fixed SST and the 4 times CO2 experiment, and it's about 0.5 watt per meter squared per Kelvin. With that adjustment and taking the radiative forcing from the doubling of CO2, which is about 3.7 watts per meter squared, we get an ECS of 6.2 Kelvin, and that's very high. Just for context, E3SM V1 and V2 had an ECS of 5.3 and 4.0 Kelvin. And this value might be lower, especially because there's studies that found that delta F actually anti-correlates with lambda it correlates with lambda such that you tend to have a lower delta T, excuse me, than you'd expect from a fixed delta F. But we still think that it'll be a high ECS that's coming from SCREAM 3 kilometers if we were to run it for hundreds of years in a coupled system. Interesting, the SCREAM 12 kilometer has an ECS of 3.7 Kelvin, but we do have some expectation that that's unrealistic, and I'd be happy if anyone has questions to elaborate that on further later. But there's still, of course, a lot of questions. That's how much confidence can we ascribe to these climate feedbacks? And that's what we're investigating right now. Now that we've run actually a global 3 kilometer model and calculated the cloud feedbacks, the big question is to what extent we can use cheaper, much more affordable versions of SCREAM, for example, the doubly periodic SCREAM or the regional refinement configuration, which Peter Bogenschutz will be talking about next all hands. Whether we would have been able to use these and run a very series of experiments to give us a good sense of what the strength of the cloud feedbacks were if we run these idealized plus 4K experiments with those configurations as well. Looking forward, we wonder how does SCREAM do with variability and extremes, and I think the decadal simulation will teach us a lot about that. And the continuous effort has been to how best we can improve SCREAM, since we know that there's still some biases that exist in the model. Again, asking, it's a very computationally expensive model, and so what is the best scientific use of the 3 kilometer global SCREAM? And so for that, I think we'd ask the larger community to help pitch in with ideas, since I think these are big questions that we still are working on and still unanswered. And so here I'll just summarize. Scream is a very computational expensive model, but we're quickly scaling up the simulation length, and that means that we can learn more and more about the climate areas that we haven't been able to tap into, large, especially climate phenomenon that take longer timescales to actually manifest themselves. Scream comes with the cost, but it also, the fact that we have 3 kilometers allows us to resolve features that everywhere that were previously unresolved, but still there is still a large ways to improve the model, and that's expected given that Scream is a model that was developed about 4 years ago, and so it's had a very short, it's quite young compared to many of the other GCMs. One of the most surprising results so far we've seen with Scream is that our 3 kilometer simulation reveals a very strong cloud feedback, and we want to figure out why that's the case. And then the decadal simulations hopefully will teach us more about how Scream is able to capture the variability in extremes. And with that, thank you for your attention, and I'd be happy to take any questions.